All right, welcome to The Explainer. Today, we're doing a first principles deep dive into a topic that, let's be honest, probably keeps a lot of you up at night: fixing broken deployments. If you've ever spent days just banging your head against the wall because your robot's software works perfectly in simulation but totally crashes and burns in the real world, well, you're definitely in the right place. We're going to look at how a production-grade software-in-the-loop, or SIL, test platform actually solves these deep-rooted integration problems at their absolute source.
Okay, let's dive into this. Here is our roadmap. We're going to quickly cover the endemic integration problem, our core thesis of pipeline over complexity, what it means to use SIL as a gate, the power of scope discipline, our architecture and tech choices, and finally, the real-world results of building a bulletproof pipeline.
Starting right off with Section 1, the endemic integration problem, or, the curses we've all whispered during morning stand-ups.
Look, we all know the pain points, right? Because they are literally felt across every robotics team. First, the classic. Your simulation passes with flying colors, but the hardware instantly fails. You merge a change validated in Gazebo, and then you just watch your physical robot veer right off a 2-meter corridor. And debugging that? It means booking bench time, fighting your coworkers for a slot, and trying to reproduce some bizarre race condition that only seems to happen when the robot is sitting at exactly 30% battery. It's expensive, and it is agonizingly slow. Then you've got pull requests that pass perfectly locally, but break the main branch the second they merge. The author swears it worked 10 minutes ago, and the crazy thing is, they aren't lying. Or how about wall clock-dependent tests? A test relies on a 2-second sleep command, which is totally fine on a dev laptop. But under CI load, the scheduler stalls, the assertion fires, and the test just flakes out. Before you know it, the team starts ignoring those red X's on their builds. Throw in the classic works on my machine environment gaps, like developing on Ubuntu 24.04 but shipping a Docker image on 22.04, and you get the terrifying reality that your release image is often completely different from the image you actually tested.
We kind of just accept all these failure modes as the cost of doing robotics, right? Actually, scratch that. They aren't the cost. They are the symptoms of a missing integration layer. As the source material so bluntly puts it, this is endemic in robotics, and we shouldn't accept it. It is absolutely time to demand a fundamental shift in how we operate.
Which brings us to Section 2, our core thesis, pipeline over complexity. This is all about completely inverting the traditional bet that most teams make.
Now, what's really interesting about this slide is how we usually frame the true cost of robotics. The real cost isn't just the algorithm itself. It's the integration, the testing, the release, and that massive, terrifying gap between, hey, it works on my bench, and it works on every single robot we ship. Most teams pour all their time and money into sophisticated robot software and just tolerate a duct tape pipeline holding it all together. But we need to flip that. A simple robot backed by a bulletproof pipeline beats a sophisticated robot held together by luck every single time. Why? Because the pipeline is the thing that compounds value over time. A world-class algorithm that you cannot reliably ship is, at the end of the day, just a massive liability.
All right, moving to Section 3. SIL, a gate, not a demo. Let's redefine what the simulation standard should actually look like.
So what do we actually mean by software in the loop in a production setting? It means you are running the entire software stack. I'm talking the exact same binaries, the exact same launch files, the exact same nodes against the deterministic physics simulator instead of your real hardware. The only thing that changes is the hardware abstraction layer. You're just swapping its backend from something like a CAN bus over to a simulator like MuJoCo. It's completely deterministic, it's repeatable, and it runs in CI on every single push.
So the crucial point is grasping the absolute difference between a demo and a gate. A demo? That's really just a visual tool to convince your stakeholders the robot can move. SIL, on the other hand, is a gate. It's a mandatory test that absolutely must pass before any code is allowed anywhere near the real hardware. It validates every commit and every release candidate without you having to risk a $40,000 rig and honestly, without the thermal noise and battery issues that make hardware debugging feel like playing roulette. Because it's deterministic, a flaky test in SIL is a real bug, not just a CI hiccup.
Moving on to Section 4, which introduces a really fascinating concept, the power of scope discipline. Think of this as addition by subtraction.
To build a pipeline this deep, you literally have to be intentional about what you don't build. In the project from our source, the robot was kept deliberately simple. It was just a differential drive platform with a LiDAR and an IMU. Look at what they intentionally left out. No nav2, because the navigation stack is this sprawling dependency surface that would just eat the testing budget alive. No SLAM, because mapping introduces a whole new universe of perception failure modes. No ROS2_control. A thinner, simpler hardware interface did the job. And no visual optimization, no camera calibration, no April tags. Literally just a simple go-to-goal P controller.
I want to pause here because this is huge. Narrow scope is what made a deep pipeline possible. All that mental energy the team saved by ignoring complex stacks like Nav2, it didn't just vanish, it went directly into building merge queues, enforcing strict sim time discipline, layering Docker images perfectly, and ensuring total release traceability.
Okay, Section 5, Architecture and Tech Choices. Let's look at the foundational stack and the real pragmatic blueprint behind all of this.
And this brilliantly illustrates exactly how to set up a reliable pipeline. For the simulator, they went with MuJoCo. Super fast, completely deterministic, and runs totally headless in CI. For the OS, ROS 2 Humble on Ubuntu 22.04 because of its long-term support and mature binary packages. Continuous integration relies heavily on GitHub Actions, with a native merge queue requiring an all-green status. And this next one is crucial. For SimTime, they use the clock topic and use SimTime everywhere to completely banish wall clock sleeps in tests. Finally, for releases, a multi-stage Docker to the GitHub container registry tagged directly by the commit SHA. The crazy part? Every single one of these choices was documented in an architecture decision record, an ADR, before a single line of code was even written.
Bringing that whole architecture to life happened in 5 strict phases. Phase 0 was repo hygiene, formatting, linting, getting those ADRs down. Phase 1 was building the robot and the MuJoCo bridge right at the hardware abstraction boundary. Phase 2 established SimTime CI, Phase 3 locked in the merge queue, and Phase 4 was wrapping up the release pipeline. It is incredibly vital to note here that Phase 0 and Phase 2 are completely non-negotiable. If you skip the ADRs in Phase 0, you have zero shared truth, and your pipeline is going to rot. And if you allow even one wall clock sleep in Phase 2, the flakiness returns instantly, and the whole system just collapses.
Finally, Section 6, Results of a Bulletproof Pipeline. What is the actual hard ROI of all this rigorous infrastructure discipline?
80 seconds. That is the median CI runtime with caching. They kept the entire CI budget under 10 minutes per PR, but hitting an 80-second median, that's a total game changer. When testing is that fast, developers are never even tempted to try and bypass the checks.
And check this out, 6. That is the exact number of real, nasty, critical bugs caught by the software-in-the-loop platform before they ever even had a chance to touch the physical hardware.
And we aren't talking about simple typos or syntax errors here. The SIL platform caught a silent quality of service mismatch. It caught a physics-induced false obstacle detection. It even caught a Docker file that was mysteriously missing a crucial package. These are complex, multi-layered failure classes that standard unit tests alone would literally never catch. You absolutely need full integration testing to expose these before they destroy your robot out in the field.
Let's move to and see how this builds to the holy grail of deployments. The release image is the test image. Thanks to this pipeline, they use the exact same Docker file and the exact same layers, all tagged by the commit SHA. So if someone asks you, hey, which code is currently running in production? Nobody has to guess anymore. It is a simple, definitive, one-line answer.
So we've seen just how incredibly powerful prioritizing your integration layer can be, and how brutal scope discipline makes the whole thing possible. I'll leave you with this question to evaluate your own team's setup. Is your robotics pipeline just a demo, or is it a truly impenetrable gate? Think about that for a bit, and be sure to check back for our next explainer where we're going to deep dive into architecture boundaries and repo layouts. Keep building,